So in this chapter, we are going to talk about acids and bases. Now, there is a typo on my slide, but it shouldn't be on your slide. It's right here. It should be chapter 2. So acids and bases are pretty common terms. You have probably talked about these since middle school or high school. You definitely talked about them in General Chemistry 1. And what we're going to do here is review a little bit about acids and bases, but then talk specifically about factors that determine acid strength. You run into acids and bases kind of all the time. You can run into them in the kitchen with baking soda, that's basic, or cleaning products, that's Clorox, that is also basic. Lemons are acidic. We also have acid-base indicators. As a reminder, those just change color based on the pH, and hydrangeas are a really good example of this in nature. So let's talk and review the Bronsted Lowry model of acids and bases. When somebody kind of generically refers to an acid and base, unless they specify, most of the time they're talking about the Bronsted Lowry model, which are named after these two fine fellows here. When we look at this, what we see, and I'm showing you this 3 different ways. We have HCl, which we can show here. We can see the Lewis structure here. Or we can see the molecular models with the dipoles, the partial negative and the partial positive drawn in. Reacts with water, there's a proton transfer. Now, I want to remind you that if we have a hydrogen without its electron, it's a proton. All right. And so what we have is an acid is a proton donor. So it will give away its proton. Right? So the acid must contain an acidic hydrogen. Now, how do we identify if there's an acidic hydrogen? Most of the time, acidic hydrogens are drawn in front of the molecule like this. We're also going to see where if you have a combination of C double bond O, OH like that hydrogen is an acidic hydrogen. So we're going to point these out as we go through organic chemistry. Okay, so it must contain an acidic hydrogen. Now, a lot of times generically, the symbol that's given is HA. All right, so that's our generic symbol. So what happens here is that HCl gives its proton to water and becomes Cl minus. Now water accepts that proton to become H3O plus. So that means water here is accepting a proton, and that's a base. Okay. To be able to act as a base must contain an available electron pair that's available to form a bond. Okay, so a base must contain an available electron pair. Now, when we talk about electron pairs here, these include lone pairs or electron pairs in pi bonds. And so that's what we see there. So when we talk about Bronsted Lowry acids and bases, I want to show you some examples. Right, so here are some examples of your Bronsted Lowry acids and bases. We can see those acidic protons highlighted in red here. The net charge here can be 0, it can be plus, it can be negative. So notice that there's a charge there. There's a positive charge here. So don't let the charge throw you off. Now, I want to talk about Bronsted Lowry bases for just a moment. You'll notice these are common Bronsted Lowry bases. These contain a lone pair of electrons or a pi bond, and the net charge may be 0 or negative. It's generally not ever going to be positive. When we talk about this, when we have charged species like that OH minus, that hydroxide ion, or right NH2, we know we cannot go into the laboratory and just measure out OH minus all by itself, because you have to measure out something with a counter ion. So, for example, the species that we would measure out would be sodium hydroxide. The sodium here is called a counter ion. It's sometimes referred to as a spectator ion. And so it's there to balance the negative charge, but their identity is usually inconsequential. It's not really going to matter. And so that means that identity is a lot of times omitted. So we see that that's omitted a lot of times. Now, maybe the burning question in your heart is, Dr. Pierce, you've shown us acids and you've shown us bases. Could there be a molecule that could be both? And you would be correct. Some molecules contain both hydrogen atoms and lone pairs. Water and ammonia are really good examples. So they can act either as acids or bases, depending on the particular reaction. And that goes for small molecules and large molecules like morphine here. And so a lot of times these guys are called amphoteric. All right. And that just means they can act either as acids or bases. So we see both of those. Here, when we talk about what makes this acidic, the hydrogen atoms here, right, on the oxygen make that morphine an acid. So we see this group where there's an O and an H. Those are also acidic hydrogens. And then the lone pair on the nitrogen, but the pi bonds, and remember we'll have pi bonds and double bonds and triple bonds, make morphine a base. We also have lone pairs on our oxygen atoms. Now, as I mentioned before, when we talk about reactions of Bronsted Lowry acids and bases, these result in the transfer of a proton from an acid to a base. Right? And these are also known as proton transfer reactions. And we are going to see these over and over and over again throughout our journey in organic chemistry. Now, when we talk about this, I'm going to show you a generic acid here. And when we want to show a generic base, we use a B with 2 electrons on it. We're going to do a double-headed arrow here, right? And what I want to show you when we talk about this is exactly the path the electrons take through this reaction. So what happens here is that these electrons on the base come out and they grab that proton, okay? And what we're doing here is we're drawing an arrow. This is what's called a mechanism arrow from the electrons to the atom that it is grabbing, okay? Now, that base is going to pull that hydrogen back and form Hb+, which is the conjugate acid. So that generic base is acting as a base and it's going to form the conjugate acid. Then what happens is, show this in pink, the electrons from this bond, when that hydrogen goes, It actually goes as a proton. It looks like that. Okay, so that means it leaves these electrons behind. It's kind of like when your friend comes and they grab you, like maybe they come to your dorm and they're like, hey, you've got to come see this really cool thing. You just kind of run out of your dorm and you leave your keys and your cell phone and your wallet and all of that stuff behind. Well, that proton gets pulled off by this base to see something that's really cool, and it's going to leave those electrons behind. And those electrons are going to then go and live on that acid. So that's going to form the conjugate base. Now, a few kind of points about this as we sit here and look at it. I want you to notice the charge on each side is the same. Okay? And what I mean by that is if you notice this has no charge and that has no charge, so the total charge on this side is 0. When you come over here, you've got a plus charge here and a negative charge here. And so now the total charge here is also 0. Now, this mechanism, so this is the mechanism where we're showing these curved arrows, obviously uses curved arrows. So I want to take a second and remind you about a few things about curved arrow notation. Now, this is also a lot of times called arrow pushing. You'll hear people talk about pushing arrows or pushing electrons in organic chemistry, and that's what we're talking about here. So a curved arrow represents the movements of valence electrons, not atoms. So we're showing how the electrons are moving. Are they going out and grabbing an atom? Are they forming a bond? What are they doing? We show that through arrows. Each double-barbed curved arrow represents the movement of 2 valence electrons. If you have a single barb like this, that is the movement of 1 electron, and you see that with radicals. Okay. A curved arrow that originates from the center of a bond represents the breaking of that bond. So let's say we have a double bond here, right? And the curved arrow starts here, right? And we end up with a single bond. That's showing the breaking of that pi bond. Those are the electrons that are moving, right? A curved arrow that points to an atom represents one of 2 things. The formation of a new sigma bond if the electrons were originally on another atom. So are we forming a new single bond? Or the formation of a new lone pair if the electrons were originally from a bond involving that atom. Now we're going to continue to look at examples of this as we go through organic chemistry. And so I wanted to have these printed really nicely for you in case you wanted to refer back to them. So let's look at another example of a proton transfer reaction. So let's say we start out with a reaction where we have water reacting with a base, which is NH2. Okay. Now, what's going to happen is the NH2 here is going to act as the base, and it is going to attack the acid. Okay. And we're going to talk about how we figured that out. But right now, just take my word for it. So if we were to draw this mechanism, right, what we would do is we would say, okay, this is going to act as a base, so it needs to grab a proton. So these electrons are going to come over here, and they're going to grab a proton here. Then that's going to pull those electrons back, and it's going to form a new sigma bond. Right? So that's a new sigma bond that it's formed. Then what we're going to see is that these electrons that make up this bond, so I want you to notice we're starting out in the middle of the bond here, and we're pointing up to the atom. We're being very specific in where we're pointing our arrows. That forms the conjugate base. Okay. We can see this. I want to do one more example. Let's say we have hydrochloric acid. So that's our acid reacting with methanol. Here, and this is a base. Now, you have to be really careful because sometimes you won't have these lone pairs shown, so you have to put those lone pairs in. We're going to draw the mechanism here. We're going to say, hey, look, we know this is a base, so these electrons are going to come out and they're going to grab that proton. And when they grab that proton, we've got Ch3O, H, and H. Now, remember, you're gaining a proton here. You're not just gaining another hydrogen, so it's going to affect the charge. And so now that oxygen is going to have a positive charge. You could stop and calculate the formal charge there, or you could familiarize yourself with common formal charges of organic molecules. Then what happens is those electrons that make up that bond come and live on that chlorine. And now you have Cl minus, okay? That conjugate base. I need to put in my double arrows here. You're going to see double arrows in your book. They're written like this. Sometimes you're going to see double arrows that look like that. Those are equilibrium arrows, right? And that's generally used between the starting material and products to indicate that the reaction can go in both the forward and reverse directions. Now, these reactions here illustrate a really important general pattern of reactivity that you are going to see all the way through organic chemistry. So here's our general pattern of reactivity. Electron-rich species, right, react with electron deficient species. That's the big deal. Things that have a lot of negative electron density react with things that have a lot of positive electron density. Just like magnets that like each other, right? That positive and negative, we know those are like each other. They're attracted to each other. We are going to see that here over and over again. Look at what I mean. When we come here and we look at hydrochloric acid and we compare the polarity, we know that, and the electronegativity, we know that chlorine here is partially negative. We know that proton is partially positive. These electrons, right, that's an electron-rich species. Electrons have a lot of negative charge density there, right? And so they will come out and be attracted to the atom that's partially positive when it pulls that back, okay? And so that's what we're talking about. Acids generally are electron deficient, and that proton of the acid has that partial positive charge. And that's why acids and bases react with each other. Now, common acids and bases from general chemistry are going to be used in the same way in organic chemistry. Hydrochloric acid and sulfuric acid are going to be strong acids. Hydroxide is going to be a strong base. Nothing is really new there. But I want to point out a few other things that you can see. When only one starting material contains a hydrogen, it must be the acid in this reaction, right? If only one starting material has a lone pair or pi bonds, it must be the base, right? A starting material with a net positive charge is usually the acid. Right? And if you have a starting material with a negative charge, that is usually the base. All right. These general kind of patterns of reactivity are going to come up through organic chemistry. If you have any questions, please feel free to stop by my office.